So when is your final, Jackson?
When?
Yeah. Is it?
Tomorrow afternoon.
Okay.
So, yeah, I just have a few questions about some problems.
Is this page 1 or page 2?
That's the first page you can do.
Okay.
Yeah, so 18 I circled. I just was wondering if we can go through that.
Okay. So f of x equals 2 sine x plus sine of 2x on the interval 3 pi to 4 pi. Okay. Such that f prime of c equals, that must be f of well, if you'll remember from your limit quotient definition, f prime of x is equal to f of x plus h minus f of x all over h as h goes to 0. But there was also an f prime of c, which was equal to f of x minus f of c all over x minus c, I believe. Let me just see if I can find that exact definition. I don't use it very often because it's just not needed very often. Hold on. I'm trying to find it in the book. Oh, here it is. It's f of x minus f of c. Hold on one second. F of x minus f of c all over x minus c. And it's the limit of that as x goes to c.
Okay.
So you know what the mean value theorem says, right?
Yeah.
What it means? Let's just talk about that. It means that if I have a function and I can figure out a rate of change, an average rate of change between 2 points, then there is some point between those 2 points, let's call them A and B. There has to be a point C that has the same first derivative as the average rate of change. The average rate of change is f of b minus f of a, that's the rise, over the run, b minus a. So as all the mean value theorem says is that there is some point where the first derivative has a slope that is the same as the average slope between a and b. There has to be. You can't have a continuous function go from a to b without having a point somewhere in between whose tangent is the same slope.
Okay.
So what they're saying is that f prime of some c equals that. And this would be c. In other words, if I find a c between a and b, and the slope of the tangent line at that c is the same as this over here, the average rate of change, then that satisfies the mean value theorem. So, first of all, let's find the first derivative of this function. That's almost always a good place to begin. F prime of x, what is it equal to?
That'd be 2. That'd be negative cosine x or just cosine x?
Cosine x. The derivative of sine is cosine. Derivative of cosine is negative sine.
So 2 cosine x plus.
So derivative of the outside times the derivative of the inside.
That'd be cosine x.
Cosine 2x.
Cosine 2x.
Times. Derivative of the inside is 2.
0.
Times 2.
Times 2.
The inside is 2x. Okay, so the derivative of the outside is cosine of 2x, the derivative of the inside is 2. So that's what f prime of x is. Now, on the interval 3 pi to 4 pi, well, notice what that is. If I go back to my original drawing, hold on a moment, let me do this. Let me move that up a little bit, and then I'll be able to move this down. On my original equation, f prime of c equals the limit of f of x minus f of c all over x minus c. Well, what is that? That's the average rate of change, right? Between 3 pi and 4 pi. Well, let's evaluate that. What is f of 4 pi?
Yeah, I don't remember any of the trig stuff, so.
Well, this is more of an algebra problem. If f of x equals 2 sine x plus sine of 2x, then f of 4 pi, I'm going to plug in 4 pi for x, right?
Yeah.
What's the sine of 4 pi?
0.
Correct. What's the sine of 8 pi?
Still 0.
Okay. So f of 4 pi is 0. What's f of 3 pi? We have to figure each of these out. What's the sine of 3 pi?
Is it the 1?
Here's the sine curve. This is a good curve to memorize. Okay, 3 pi is the same as pi, right?
Yeah.
This is pi right there. So it's 0 again there. But now it says the sine of 2 times 3 pi. Well, that's 6 pi. That's the same as 2 pi. Okay. So this right here is 0 minus 0 all over pi. So that's 0. Okay, so I can say that f prime of some c has to be equal to 0. So we need to find the c that's equal to 0. In other words, the slope of this equation between 3 pi and 4 pi needs to be 0. It needs to be a horizontal line. Okay? And it's like if I drew the curve, that's not what this curve is, but between that point and that point, the average change is 0, right?
Right.
Well, there's 2 places where that happens, there and there. So if I was solving this, that would be one point, that would be another point, where my instantaneous slope is equal to the average slope.
Okay.
Well, let's find out what f prime of these numbers are. Remember what f prime of x is.
Yeah.
Where did I write it? Right here. F prime of x. So I have to find some x that's equal to 0, because I know that's what the right side of the equation is. The right side of the equation is 0 minus 0 all divided by pi. So I have to find some c, and f prime of x is this, that's equal to 0. Well, let's first of all divide everything by 2 to get rid of those 2's there. So now I have cosine of x equals minus cosine of 2x. Cosine of 2x, there's an identity for that. What is it? Which one? There's 3 of them, actually. I want to use the one that has nothing but cosines in it, which is this one. It's minus, but it's 2 cosine squared x minus 1. That's the cosine of 2x identity I'm going to use.
Okay.
The reason I'm going to use that one is because I'm going to be able to solve this equation now. That's a quadratic in cosine x. And once I can solve this equation, I can figure out which values satisfy this. So, and I need it to be between 3 pi and 4 pi. So, first of all, let's eliminate the parentheses here. What do I get? Right?
Right.
Now I move everything to one side because I have a quadratic. And then I solve it. Well, how does that solve? 2 cosine x minus 1 times cosine x plus 1. That gives me the proper middle term. How do I solve those two?
You do, well, isn't cosine x plus 1 just sine?
No,
Or is that,
hold on. This is the fundamental theorem of algebra. I got two things that multiply together equaling 0. Therefore, I set that equal to 0 and I set that equal to 0, and there's my solutions. Okay, so this equaling 0 means cosine x equals 1/2. This equaling 0 means cosine x equals -1. Okay, so now I can figure out my x. Where does cosine x equal 1/2 in this interval? Well, first of all, where would it equal 1/2 in the first quadrant?
Would it be at,
60 degrees.
Okay.
Okay, this x, cosine x equals -1 at 180 degrees. Okay, but neither of those answers, and in fact all my answers are in radians, so let's convert this to radians. That's pi over 3, and that's pi. So those would be my answers, except they're not in this interval. Notice that interval is the second unit circle. What's the equivalent of pi over 3 in the second unit circle? Add 2 pi to it.
It'd be, I'm not sure. I don't.
If you add 2 pi to pi over 3, you get 7 pi over 3.
Okay.
Pi over 3 plus 2 pi, well, I can write 2 pi as 6 pi over 3. Pi over 3 plus 6 pi over 3 is 7 pi over 3.
Yeah.
And pi is 3 pi if I add 2 pi to that. So both of these should be the answer. Well, let's see. Well, first of all, we're looking where f prime of 7 pi over 3 has to equal 0. Is that true? Well, let's see. In other words, maybe I made a mistake. So here's our function. Here's what f prime of x is. Well, let's figure out what f prime of what I think the answer is, 7 pi over 3. Is that equal to 0? Well, 7 pi over 3 is the same as pi over 3. So we have the cosine, 2 cosine of pi over 3 plus 2 cosine of 2 times pi over 3. Is that equal to 0? Well, let's see. Cosine of pi over 3, that's 60 degrees, that's 1/2. So we have 1 plus 2. Cosine of 2 pi over 3 is -1/2. Yes, that is equal to 0. So, I see what I did wrong. Notice that 7 pi over 3 is not in the interval. That's not between 3 pi and 4 pi. If I draw a unit circle, cosine is positive here and here. So this is the part that they're looking for, the third and fourth quadrant answer. So I need the equivalent fourth quadrant for 7 pi over 3. And that has to be, let me think for a second. Let's see, that would be 12 pi over 3 minus a pi over 3, 11 pi over 3. That, if you fill that in, 11 pi over 3, right here, you will get 0. In other words, f prime evaluated at 11 pi over 3 is equal to 0. And the mean value theorem does apply. In other words, this came out to be 0. So the mean value theorem says that somewhere between 3 pi and 4 pi, there is going to be a point where the derivative evaluated at that point is going to have the same slope as this average change. This average change was 0. So what C between 3 pi and 4 pi is f prime of C equal to 0, and it's A. Mean value theorem does apply, and the point is 11 pi over 3. And the easiest way to prove it to yourself is with this equation. In other words, you want f prime evaluated at 11 pi over 3. Is that equal to this expression? Well, we saw that this expression is equal to 0, and I'm telling you that f prime of 11 pi over 3 is also equal to 0.
Okay.
Wow. Hope that they don't have very many problems on the test like that.
Yeah.
Not that that's that hard. The concept is relatively easy, but they've made it extremely tough by making the interval 3 pi to 4 pi. You know, had they made the intervals 0 to pi, our answer would have been pi over 3 instantly. The fact that they make this interval the second half of the second unit circle is what makes this a little tricky.
Okay.
Not that tricky. The concept is the same. The concept's very important here. That there is a slope somewhere between those 2 points that is the same as the average slope between those 2 points. That's the concept of the mean value theorem. You just have to find out what it is, and that's what we did.
All right. Yeah, I think.
Second page.
Yeah. So just for that, so just finding the average rate of change. And then plugging those values into the derivative.
No, you got it. There's 2 steps here.
Okay.
First of all, find out what this is. But there's f of x, okay?
Okay.
So what is f of 4 pi? You plug in 4 pi wherever you see x. Okay, so evaluating the right side of this equation is relatively easy.
Okay.
And when you do so, you get 0.
Okay.
That means that somewhere between 3 pi and 4 pi, the derivative of this function will have a value of 0. That's all it means. That's what the mean value theorem says. You can't get from 3 pi to 4 pi, which has an average change of 0, without seeing a slope that has 0.
Okay.
Okay? Well, take the derivative of that function, which we did, and set it equal to 0 and solve it and find the answer that's in that interval. There's lots of answers. There's an answer in the first quadrant. There's an answer in the fourth quadrant. But this is the eighth quadrant where we're going to find our answer. 11 pi over 3 is the eighth quadrant. You know what I mean by that?
Yeah.
Okay, that's the eighth quadrant. The end of the eighth quadrant would be 12 pi over 3. So in the eighth quadrant, cosine is positive, but it's also 0. In other words, if you take f prime of x and you substitute 11 pi over 3 for x, you will get 0. That's what we did. Here's the integral right here. F prime of x was equal to 2 cosine x plus 2 cosine 2x. Well, if I want to know what f prime of 11 pi over 3 is, I substitute 11 pi over 3 for x. You go through that and you're going to see that the instantaneous is 0 at 11 pi over 3. That's what the mean value theorem says, is that there is a point where the slope will be 0. In other words, let me try to define this for you a little bit. What's the average rate of change between there and there? Rise over run.
So it'd just be 0?
Yeah, the rise is 0. I don't care what the run is. If the rise is 0, the average rate of change is 0. Okay? What that's saying is that somewhere between those 2 points, there is a slope of 0. Well, we see lots of them. We see one there, we see one there, and we see another one there. In other words, I cannot get from this point to this point without seeing a slope of 0 in between. There's no way. I mean, if I didn't want to make it continuous, maybe I could. There you go. But the mean value theorem only applies if it's differentiable over that interval. And if I had a corner like that, that's not differentiable across that corner. So mean value theorem would not apply. Mean value theorem applies only if the function is smooth and continuous. Well, now I have a smooth continuous function, but there's definitely one spot there where the instantaneous rate of change is the same as the average rate of change.
Okay.
All right.
Yeah. Yep.
I went to a different page. Is this the next page you want to look at?
Yeah, just limits and optimization. I just was having troubles with.
Okay. Hold on a moment. Let me close my door here. All right, find the limit as x goes to infinity. What happens to that expression as x goes to infinity? We have 3 plus 2 over x. What's that exponent? 8?
To the 8th.
What is it?
The 8th.
Yeah, it doesn't really matter what it is, as long as it's a positive number. What happens to this expression as x goes to infinity? If the bottom blows up, what does the number do?
It gets smaller.
Okay, so what does it go to? What's the limit?
Negative infinity?
0.
0.
It gets smaller, but it doesn't go negative infinity. It goes to 0. I mean, think about it. If I start putting in large numbers, okay, there's a large number. Now let's try putting in a larger number. Okay, now let's put in a larger number. Notice where we're headed. We are headed to 0.
Okay.
Okay. If your denominator blows up and your numerator is a constant, you're always headed to 0. There's no other place to head. Your numerator's not changing. Your denominator keeps getting bigger. So if this is headed to 0, the whole thing must be headed to... Where's the whole thing headed?
That's 0 as well, or?
No, only part that's going to 0 is this part. Headed to 3, yeah.
Okay, I see.
See it?
Yeah.
All right. So D is the answer there. And this one.
Okay.
What is this equal to? I'm going to give you another problem first before we do this. What's that limit equal to? In fact, let me change this even more. I'm going to make that squared. I'm going to make that squared. And I'm going to subtract 100x. And here I'm going to add 1000x. In other words, these things do nothing to the limit. The limit is based only on the highest degree polynomial. And if the degree is the same in the top and bottom, then the limit goes to the ratio of the coefficients, the same as the horizontal asymptote. Remember, if we were doing a horizontal asymptote there, it would be 2/3. Well, okay. Horizontal asymptote means what does the function do as x goes to infinity? So horizontal asymptote is the same as this question. Now, the question's a little more complicated because we don't know how to take the square root of that. But I can see that the square root of that is 3x. And we have a minus 4x there. So where do you think this limit's going? In other words, we have a minus 4x is the highest degree in the numerator. And if I just take the square root of the biggest thing in the denominator, I get 3x. So where's that limit going?
Minus 4/3.
Yeah, now the question is, if I add that 2x to the 3x, I would get 5x, and it would be minus 4/5, but that answer isn't on there. So I'm going to assume that we can do it this way, which is to ignore that term. Oh yeah, because when I take the square root of that term, it's going to be square root of x, which is a lesser degree than 3x. So this is definitely correct.
Okay.
In other words, this is the same problem as if I said, what is the limit of minus 4x plus 3 over 3x plus 2x to the 1/2, right? That's not exactly what the square root of that is. But given that the only thing we care about is the highest degree polynomial, then I can take the square root of just that term. And the square root of just that term is 3x. And so this is a reasonable approximation for what the denominator would become. And now I have my highest term polynomial as x, and the coefficients are minus 4 over 3.
Okay.
All right. An optimization problem. A rectangular page is to contain 81 square inches. Margins on each side are 81 square inches of print. So the inner box is 81 square inches. This measurement is 1 inch. This measurement is 1 inch. With me?
Yes.
Find the dimensions of the page such that the least amount of paper is used. If I call this x and this y, the amount of paper used is what?
X times y.
Okay.
Oh.
Yeah?
Yeah.
No, you're right. That's the function we want to minimize. Well, what else do we know here? In other words, I can't take the derivative of this area function because it's a function of two different variables. So I need to turn one of these variables into the other one. Well, what's another equation that I can use? What's 81 equal to?
Would it be x minus 2 times, would it be y minus 2 as well?
Correct. So there's our second equation.
Okay.
Now, what we're going to do is we're going to solve this for y and substitute it into that. And then we're going to be able to take the derivative of it, set it equal to 0, and solve for what value of x works.
Okay.
Well, the easiest way to solve that for y is to do this. Correct?
Yeah.
So all I have to do is make y a complete function of x. And I've done it.
Wait, is it just, how come it's x minus 1 but y minus 2? Like, how come it's not x minus 2?
It is. I accidentally erased it and then I forgot to change it properly. There you go. Thank you. Okay. So now I go to my area function, the function that I'm trying to minimize, and I'm going to make that area function a function of x. Well, it's x times y, only now y is 81 over x minus 2 plus 2. That's my new y. So here's the function I want to minimize. The area of this sheet of paper. I have no idea what x and y are, but I know I want the smallest possible area for this large sheet of paper. Well, as a function of x, what do we have? We have 81x over x minus 2 plus 2x. So far, so good?
Mm-hmm.
It's a prime of x.
Let's see. It would be x minus 2 times 81 minus 81x times 1 plus 2.
Hold on, you need a bottom to that quotient.
Oh, over x minus 2 squared.
Now I'm going to set this equal to 0. The only way a quotient can be equal to 0 is if the numerator is equal to 0. If I tell you x over y equals 0, I don't care what y is, x has to be 0. Okay?
Okay.
So, however, in this case, I need to move that minus 2 to the other side. Okay, so what do we have here? We have 81 times x minus 2 minus 81x equals, I've moved that over and I've multiplied both sides by that denominator. With me?
Yeah.
In other words, all I'm doing is solving this equation. Now I have 81x minus 162 minus 81x equals this quantity here. So the 81x's cancel, and I get minus 162 equals minus 2 times x minus 2 quantity squared. Divide both sides by minus 2. Get 81 equals x minus 2 squared. Take the square root of both sides. You get x minus 2 equal plus or minus 9. And you get x equal plus or minus 9 plus 2. Which means x is equal to either 11 or x is equal to minus 7. Well, you can't have a negative dimension, right?
Yeah.
So x equals 11. And that's the answer. In other words, notice that that gives you 121 square inches for the page, right?
Right.
And if I take an inch off of all sides, the inside rectangle is, or square is 9 by 9, which gives you 81 inches. None of these other answers work even. That's bigger. That's bigger. Well, that's bigger and doesn't work. That's bigger and doesn't work. That's smaller and doesn't work. Doesn't give you an inside square of 81 inches. And that's bigger and doesn't work. So there's only one answer that works. And that is a page that is 11 by 11. Notice that if this outside page is 11 by 11, the inside page is 9 by 9. Right?
Right.
Area equals 81.
Okay.
All right.
I just had a question real quick
Sure.
about So like like the limits we were talking about earlier, like that had to do with M behavior.
Okay.
So what if like the coefficient on top is greater than or less than the one on the bottom? Or sorry, the exponent.
Something like this.
Yeah.
You have to first divide the bottom into the top.
Okay.
And you will come up with a linear function, which is the equation of the oblique asymptote. In other words, when you have a function like that, you have a horizontal asymptote at plus and minus 1, and you have an oblique asymptote, which is some linear equation that looks maybe something like that. Okay?
Okay.
And then the function goes in between or on this grid of asymptotes. In other words, this function might look something like that. And then down below, you might have that. And then up above, you might have this. So if the top is bigger than the bottom, you don't have a horizontal asymptote. You just have an oblique asymptote and a vertical asymptote. And the same with limits. If I'm taking the limit of this as x goes to infinity, well, what is it going to be? Forget my graph, but you can figure it out from my graph also.
That'd be infinity as well?
Yeah. In other words, if the numerator blows up and the denominator doesn't, in other words, the numerator is going to blow up faster than the denominator, right?
Right.
Which means the whole thing blows up.
Okay.
Okay. Make that a squared, and now they're basically the same, but the negative 1 doesn't affect anything. The only thing that really matters is that, and that ratio is 1. So the limit of this would be 1. It's always the limit of it's always the ratio of the coefficients if they're the same. Now let's do this. Now let's make the bottom bigger than the top. Well, now what blows up, the bottom or the top?
The bottom.
So this goes to 0.
Okay.
So if the top blows up, it goes to infinity or negative infinity. And if the bottom blows up, in other words, if I put the cube back on there and I want to know what happens as x goes to negative infinity, well, the function goes to negative infinity. It blows up on the negative side. Okay, but if I say as x goes to positive infinity, it blows up to positive infinity. As is shown by this graph, notice that the function approaches this slant asymptote, and that means that as I go to infinity on the x-axis, my y goes to infinity. So that's why the curve looks like that. But we don't need the curve here to figure out what that is.
Okay.
If the powers are the same, just take the ratio of the coefficients. If the numerator is bigger than the denominator, the answer is infinity. If the denominator is bigger than the numerator, the answer is 0. And that's the only 3 situations you're really going to be faced with, I believe.
All right.
Okay. I mean, if I had, say, x to the third over x, well, clearly the numerator is blowing up. If I had x to the third over x to the fourth, the denominator is blowing up. This thing's going to 0, not infinity. And if I had x to the third over x to the third, regardless of what else you have, I could have 1,000 x squareds there. And if that coefficient is 2 and that coefficient is 3, then this limit is 2/3.
Okay. Yeah.
All right, let's see. We got 5 minutes here. You want to look at any of the others?
Do you have I don't know, like an easier optimization problem? Just another one to kind of go over?
Got the most basic one of all.
All right.
The open box problem. It's awful similar to the other one. You want a different kind? Let me give you the farmer and the corral. Is that okay?
Yeah.
That's at least a two-variable problem. The problem with the open box, in other words, if you have a rectangular piece of cardboard and you cut out a section that's X on each corner, and you say, I'm going to make a box, I'm going to cut out these corners, and I'm going to fold it along the dotted lines, and I'm going to have a box that's going to have a certain volume. There won't be any top on the box, but it'll have a bottom, right?
Right.
Well, the volume of that box is the base times the width times the height. Well, let's say I'm dealing with a piece of 11 by 8 paper. So the volume of the box is base, width, height. But in my case, the base is 11 minus 2x. The width is 8 minus 2x. And the height is x. So immediately I have my volume function 100% a function of x. That's why this is the easiest optimization problem there is. You don't have to use any other equation to turn volume into a complete function of x. Now it's simple. Multiply out, take the first derivative, set it equal to 0, and then it'll tell you what your x is. Okay? Let's take it up a notch where we add a second variable. You have a farmer, has a house. He wants to put a barn or a corral on the end of his house that only has 3 sides on it. His house is going to be one side. Okay? And he has 2,000 feet of wood. There's this a very practical problem. In his house, he has 2,000 feet of wood. How does he build the largest area corral next to his house with these 2,000 feet of wood?
Okay.
Okay. Well, the very first thing you want to do is define the function that you're going to optimize.
Which is
what? What am I optimizing?
Area?
Yes. What's the area of this corral? Let's assign some variables. That's x, that's y, that's x. So what's the area function?
X times y.
What other function can I talk about given the fact that I have 2,000 feet of wood?
2,000 equals 2x plus y.
That allows me to define y as a function of x and substitute it into my area function. In other words, y becomes 2,000 minus 2x, right?
Right.
Now I go into my area function and x, and instead of y, I'm going to write 2,000 minus 2x. Now I have my area completely as a function of x, and I can take the derivative of it. What's the derivative of that?
X times minus 2.
Well, let's distribute this.
Okay.
2,000x minus 2x squared. Now take the derivative of it.
2,000 minus 4x.
Set that equal to 0 and solve it. That's the optimum corral, is 500 there, 500 there, and 1,000 feet there. In other words, a rectangular shaped corral, and that gives you an area of 5,000 square feet, or rather 50,000 square feet. And there's no other design utilizing exactly 2,000 feet of wood that'll give you a bigger area. Not as long as everything is a straight line. If this 2,000 feet of wood could be turned into a circle, then a circle is more efficient and would actually give you a bigger area. But if you are assuming that it has to be straight edges, that's the best we can do.
Okay.
Okay? And this really is your classic optimization problem. Mainly because you start out with a function of two variables, and yet you're given enough information that you can come up with another equation for those two variables. And now you have two equations, so you can actually make your first equation a function of one variable only. And that's the key in all of these optimization problems, is regardless of how your function starts, you need to be able to convert it to a function of one variable. I cannot take the derivative of this as long as I have an x and a y over there.
Okay.
I mean, you could using implicit differentiation, but that's not what you do on these problems. You turn it into a function of one variable only. And that's the key. All right?
All right.
Well, Jackson, good luck. You tested. You're off school today, right?
Yeah, I got a snow day.
Does that move your test back one day?
No, they just put a bunch of tests together tomorrow, so.
Right. I was kind of surprised they canceled school today everywhere, just because I knew finals were here. That's got to make it extremely problematic for the school system, I think.
Yeah, and studying for all of them at the same time.
Well, it was probably a big break for most of the students because it gives you a complete day off to study.
That's true.
Right? I mean, I bet that there was a huge sigh of relief this morning when everybody found out school was canceled.
Yeah.
They could stay home and study all day for the finals.
That's true.
So, anyway, I hope this helped you. And
Yep.
Good luck, and I'll probably talk to you next semester.
Yeah. All right.
All right, Jackson. Have a good one.
Yeah. Thank you.
You're welcome.